This video will cover section 2.6, part B, and this is where we left off from part A video. And so the connection between pre-cal and calculus comes here. So in calculus, we look at the limit of a function. And sometimes, even though the function is not defined for a particular x value, we can still find a limit of that x value. And so here it's saying, what is the limit of the function as x approaches a from the right, which is the same thing that you do here, but in pre-cal. So this is pre-cal, and then we do this in calculus. But it is the same concept. We look at the behavior of the graph. Is it growing it's without bound, or is it decreasing without bound? Okay, example 2, we went over the domain at the beginning, right? And we were solving equations such as that. By the way, this is another way to solve it. You could take the -9 across, and then you will take a square root. And so that will be x cannot equal positive or -3, right? So that was those were the exclusions of the domain. But if we want to talk about vertical asymptotes, which I will be abbreviating with VA, we're going to say those are the lines. They're vertical lines, first of all. So x equals 3 and x equals -3, which were the exclusions of the domain. Same thing for this one. If we take x squared minus 9, in this case I'm saying 0 because I'm finding the vertical asymptotes. So we could solve it the same way we did here, or we could factor x plus 3, x minus 3 equals 0. So then we will have x plus 3 equals 0, and x minus 3 equals 0. So therefore x equals -3, and x equals +3. So those will be, again, the vertical asymptotes for that rational function. And the one that we have here, we already found that there were no exclusions in the domain. In fact, the domain happened to be all real numbers because there was no x value that could make that denominator equal to 0. Because of that, we have no vertical asymptotes. And we have the graphs here for you to look at. So here we have 2 vertical asymptotes. By the way, when you graph this on the calculator, you're not going to see the vertical asymptotes or the horizontal ones. So that's why you have to learn how to find them by hand. Now here on this one, remember how we got 2 values, right? But here we're only seeing one of them as the vertical asymptote. So what happened there? So let's look at it again. And if we were to factor the denominator, and then you look at the numerator and denominator, what will happen with x plus 3 on the top and bottom? Cancel out, or together they equal 1, right? They equal 1, so we can cancel. So what that means, that is called a removable discontinuity. Why? Because that function became 1 over x minus, no, not minus, which is the one? X minus 3. And so because of that, the only, well, first of all, that domain, we still need to exclude both values, this one and this one. But the vertical asymptote is only that one. But since we excluded that other x value from the domain, at x equals -3, what we have is this open circle. You guys see it on your graph? It's tiny, tiny, tiny. And so an open circle means that it's not included. But because you were able to factor and cancel something out, you don't have a vertical asymptote anymore, but you still have to have that open circle. Okay. So a value where the denominator of a rational function is 0 So please copy that statement. A value where the denominator of a rational function is 0 does not necessarily result in a vertical asymptote. So if we were to factor the numerator of this function, it would be x plus 2, x minus 2 over x minus 2. So that would turn into x plus 2. Right, so we went from a rational function, because it is the ratio of two polynomials, to something that it just looks like linear. And that's why the graph is just a line, like that. But if you look at it closer, it does have a discontinuity. It has this open circle here for that x value that will cause the denominator of the original to be 0. So if you were to look at the original function here, and you try to find f of 2, and you put a 2 here, you will cause the denominator to equal 0. So on the original function, you can see why it is undefined clearly, right? On the linear, you cannot, but you still need to be careful. Now, why is it not a vertical asymptote? What do we call it instead of a vertical asymptote? So it is a removable discontinuity. Okay, now the x equals 2 causes the denominator to be 0, but there is a please make sure you copy every single definition here, word by word. And just to recap what we did at the end, we factored a function, graphed it, it looks like a line, but it does have an open circle here. That would be the removable discontinuity that happens to be at x equals +2. And that comes from this factor that was canceled out if we were to equal it to 0. Then the last thing on this slide will be the horizontal asymptotes of rational function, which will be horizontal lines, and that is why we have the y equals b equation, because those will form a horizontal line. And whatever the number is, we're generalizing it with the letter b, but that will be a numerical value, and that will be where the horizontal asymptote happens. In this case, this horizontal asymptote was crossed. That's okay. And the first two were not crossed. So horizontal asymptotes, they may or may not be crossed. Vertical asymptotes will never be crossed. And also making the connection to calculus, we have here that arrow notation. It could also be translated to the word limit. So as x approaches infinity, the function value is approaching, in this case, the asymptote value, which will be the letter b. So this concludes the video 2.6 part B.